Got it. Got it. Got it. Okay. So now let's share my screen here. Okay, this is the first class. Did it. Okay, so for the chapter 5, we are talking about the, I don't know what's happening, but okay. So for the chapter 6, we are learning the computer arithmetic. So as you know, in the computer, the numbers not stored in the formats we usually use. It's not in the 10 base, it's in the 2 base, it's the binary, right? So let us take a look at the binary representations first. So the floating point numbers, if you use the programming language, and then you will know there's different types of the numbers, floating point number, the integer numbers, and so on and so forth. So here the floating numbers could be any of in any of the base, maybe base 10, and then that is their normal numbers we have used in the daily life. So for the 10, the 10 base, and then sometimes we have like the numbers 10.1234, and then this is the common way we represent the numbers. But in the computer, it would use, this is the 10 base with the 10 base, and then each for here, the 1 here, and then it can be represented in this way, right? 10 pi times 1, and then this is the digit here, and then this is a 10 base, and then plus the 0, and then this is the digit here. But here, this one is 10 to the order of 0, and then times 0, and then plus for this place, and then is the first place after the decimal point, and then this one is the digit here is just 1, and then this is 10 negative 1, and then this one is plus 10 negative 2, and then times 2, and then 10 negative 3 times 3, and then 10 negative 4 times 4. This is the usual way we represent the numbers. But in the computer, we use the binary representation. So here in this chapter, section 6.1, we focus on the binary representation. So this is examples for the binary representations. Binary representation. So let's take a look at this number here, 1.0101, and then is in the with the base 2, and then times the 2 to the power of 2. And so for here, what do we have? So if you take a look at here, we change the base. This is the base 10. So we have 10 to the power of 1, to 10 to the power of 0, 10 to the power of negative 1. So we do the same thing here, but we change the power, the base here. We change the base to 2 here. So for this one, it's just a digit. We have the digit here, and then this is 2, and then to the order of, because this is the decimal place, and then this one is the place right in front of the decimal, and then the 2 order here, the order for the 2 exponential here, it should be 0. And so here we have the 2 to the 0 here. And then for the next place, we have the place right after the decimal point, but the digit here is 0. And so we have 0. This one is numbers, the first place after the decimal point. And then so this one is not 1, it's negative 1. And so this one is negative 1. And the next one is the 1 here. And then we just copy the digit here. And then this is the second places after the decimal point. So that is the -2. And this is the 0. The fourth place is here. The third place is here. And then the digit here is the 0. And then we have the 2 to the -3. And for the last digits is the fourth places after the decimal point. So we have 2 to the -4 and then times the digit over there. And then that's just 1. And then we also have something similar to what we have in the scientific notation here in the 10 basis. Sometimes we write the 100 in terms of 10 to the power 2. And here we also have the exponentials representation here. We have the 2 to the power 2. So we have 2 to the power 2. If you do such calculations in your calculator, and then it will give you the numbers in the 10 basis. And at the end, after some calculations, you will get this number in the 10 basis. This is the common ways we use in the daily life, and then this is 5.25. But if we represent it into the binary representation, and then this is the way we represent it with the scientific notation, the exponentials here. Any questions?
Here are the 2 to the -power 1. Does it equal to 1.5?
This one?
Yes.
The 2, yes, 1/2, yeah. And then this one is 1/4, 1/8, yeah. But because this is a binary representation, we have more places after, maybe we have more places after the decimal point. So we use the -1, -2, -3, -4, and then this is the 4 places after the decimal point. So this is a convenient way to convert the binary representations to the 10 basis representation.
So the base here is 10 instead of 2 for the 5.
This one is the 5.25 is in the basis of 10. This is the usual way we convey a number. This is the daily life use. You pay the $5.25, and then that is the real numbers we use in the daily life. But you cannot tell the registers that I want to pay 1.01 in the binary representation, and that the supermarket staff cannot understand. But the computer can understand this language. The binary representation, it cannot represent this 10 basis, because in the computer language, you can only represent a number with 101010. So this is the way how the computer represent the numbers. So let us take a look at the general way to represent the numbers in the scientific notations in terms of the binary representation. So for any real number, we'll have non-zeros x, and we can represent the x in this way, plus or negative, because we can have the positive number or negative number. So it could be have a sign in front of the number, and then we have a s times the 2 exponential here, and then the s is between the 1 and smaller than 2. And this is the scientific way to represent a real number in terms of the binary representation. And we call the s is the significant. This is not significant, and then we change this one letter over there, and then it's significant. And because it has all significant information in this number, besides the exponentials. So another important information is the exponential. So we call the E exponent. So the S could be in this way, because the number is between, the S is between the 1 and 2. It could be 1. And then the S is in this format, 1.B1, B2. This is the number, the digits in the first place, second place, and so on and so forth. And then it's in the binary representation. And because it's binary representation, which means that the BI, the digits here, B1, B2, B3, it could only be 2 options, 0 or 1. And this is the scientific way to represent a binary number. And significant, it has almost all the important informations. And also we need the exponent as well. Any questions? If no, so there's one question here. So how the computer store the number? So how does computer store numbers? And then, as I said before, the computer only recognizes the 1010 numbers. It's just one. It's like the lock. You can only zero or lock or unlock, and then so there's only a 0 and 1 there, and just 2 status. And the scientific notation with finite numbers of the binary digits in the computer. There's one example in the computer, and then this is an example how the computer store the number. And it just have the notation, the sign positive, and maybe you have a negative number, and then there's a sign represent the negative. And this is one example. And then we have 1, 0, 1, 0, 1. And then also there's one places to store the exponent number. And then that is the exponent number here. And then this is how the computer store the number. 1, because the 1 is fixed, so that we just need to have the information about the numbers after the decimal point. And then so we just need to know the 10101, and then the computer know, okay, my significant is 1.10101. And then the computer also need to know the exponent, and then the exponent is 1, and then now the computer know, okay, this is my number, and then I can just store the number with 1, 2, 3, 4, 5, 6 bits. And this is how the computer store the number. And you have already, maybe you have already heard about this. This is a single precision, and which means that the numbers, the computer has 32 bits to store one number. And then what about the double bits? The double precisions means that the computer has 64 bits to store one number. And then you could see for the 64, the double precisions is more precise than the single precisions. You can store more smaller numbers in these double precisions. And in the computer, we have 1 bit for the sign, and then 52 bits for the. And we have, so for the double precisions, we have 1 bit for the sign, either plus or minus. This represent positive and negative. And then for the S, so for the S, we can have 52 bits to store the, this is the significant. And for the exponent, and then we have 11 bits to store the exponent. So let's take a look how many finite numbers we can represent with this computer, because we already know if this is double precisions, and then we have 1 bit for the sign, and then 52 bits for this one, and then the 11 bits for the exponent. So let's take a look how many finite numbers can a computer store. So this is the questions. So float point numbers in the computers are finite. And the question is that how many numbers are there? So let's take a look at here. We have we only consider the double precisions. Let us take a look at exponentials, and then the exponentials, the maximum of the exponentials we have, because we have 11 bits, right? So the exponentials we have here could be 11, and so here we have 2 times 2 to the power of the 2048. So the exponentials could be as big as this, 2048. But this is theoretically, and then in fact, we can shift the number a little bit so that we can represent the next number, the negative exponential. And then also we have the positive exponentials. And in practice, we have the exponentials minimum is the negative 1022, and then the exponentials maximum is 1023. And there are 3 numbers missing here, two numbers missing here. Maybe it is used to store other information in the computer, but in practice, we have the exponential minimum is this number, and then this is the exponential maximum. And then we just shift this Emax a little bit. So what do I mean here is that, so for the exponentials to 11, originally we have the, let me see, 2 to the 0, we have 1 to the 2048, but we shift it a little bit. Shift this interval a little bit so that we can represent the number, the exponentials between the 1022 and the 1023. We just shift it to the left on the x-axis so that we can represent the negative exponentials as well. Does it make sense? So we have 11 bits to store the exponentials, exponent message, but we shift it a little bit, and now we get the negative exponent, so that we have the negative exponents in these numbers, in this part. Does it make sense? Yeah. Okay. So here we have. So for the exponent, the numbers of the minimums we can have in the double precisions is the x. And then is the, we have the absolute value here because you can also represent a positive number or the negative number, because we have 1 bit there to represent the sign here. But what about the minimum of the absolute value of the x that we can represent with the double precisions? The minimum numbers the minimum of the absolute value number here is the 2 to the power of the negative 1022. That is the exponentials we got here. This number is around it's a very small number, and then you can do a very good precise number here. And then what is the biggest numbers we can have in the double precision number? We can have this number. This is the absolute value numbers. This is a 2 to the 1023. This is very big numbers here. And this is how, that's all the number we can represent with the double precision number. Does that make sense? This is all the numbers we can have in the double precision number. Sometimes if you are doing some calculations, especially the iterative method of to solve the linear equations or some nonlinear equations, and the computer would give you an error. It says it's overflow. Sometimes your algorithm could be wrong, and sometimes maybe the solution is just blowing up. Blowing up, it means that the solution or the simulation is going to the infinity. The number is going to infinity. So, but what we know is that the computer only have finite numbers. We only have the maximum number here, and then we have the minimum number here. So what would happen if the numbers is really big? The computer would just tell you, sometimes you are doing the computations, and then the computer would tell you, overflow. This is the error message. And it means that you get a number that is, you have a number that cannot be represented by the computer. And then that is the number, if you are using the double precision number, and then it means that you get a number during the simulation that is bigger than this number. If you have an error, it says it's underflow. Under the flow, it means that we don't have, the computer cannot represent that number because it is so small. It's smaller than this number. And then you would get such an error message from the computer because the number you get is smaller than this one. Does it make sense? And sometimes this is the error message. This is some interesting fact about the computer. It gives you overflow, underflow, and that means that your simulations give you some numbers that is not accessible by the computer. But sometimes the number is not so small, and then it could be, let me see. You have already seen this in your Excel, and then this is really frustrating, but you can address it. And then when you're using some Excel or some computer to calculate something, and then you might be getting a number 10 to the over 6 or 8, but the computer will only tell you it's 0. And what's that called? It called rounding up. The computer automatically round up the numbers for you. So now let's go to the next sessions, and it's about the rounding up and machine precisions about in the computer. And so here we have the rounding up. So a lot of time it's really important to tell your computer how much precision you want. And it will also affect the calculations, the simulations precisions. And so let's see. So let's just stick on on the binary representation at this moment. And then this is a binary representations for one number, one real number. And then it has an exponent here. So if we have an infinite point up to the decimal points, finite digits after the this decimal points. And the question is that how to approximate this x well? Using the finite number of bits. So we only have 64 bits, right? And then if we have infinite numbers, digits after the decimal points, and then how can we stop somewhere and then to get a approximation of x, and then that approximation is a good approximation? How can we tell that is a good approximation? So let us go back to what we have in the 10 decimal points. Where's my talk? So let's go back to the old days when we use the 10 points, the 10 base. So we have, let us say this is 10.4. Would you just round it down or round it up? Will you tell me? Round it up or rounding up to get an integer representation? Which one would you choose to get a better approximation? 10, because the distance between the 10 and this number is 0.4, and this one is 0.6. And it's always said this one, the distance is closer. So we use the 10, right? What about if I change this number to 6? Then obviously the distance between this one is 0.4, and this one becomes 0.6, and you would choose the 11 one. So we would decide the distance between there. We make the decisions based on the distance between this number to the neighbor integers. So we use this idea as well in the binary representation. So for example, if we have the 1.0100101, and we want to run it up to, this is in the 2 base, and we want to run it up to the 5th place. We only keep the 5 digits up to the decimal points. And how would you run it out? So we only want to keep the 5 decimal places here. And then we only want to keep 5 places. Will you run up or run down? It depends on, so we have the integer here, right? And then we look into the next numbers. That is a 0.4. So if we want to decide whether we need to run up or run down, and then, so we only keep 5 places. So we need to look into the numbers we have here. It's 1, right? It's 1. And how many options could we have in this number? It's either 0 or 1, but 1 is the bigger one, right? So now we run it up. So because the B6 equals to 1, and then we run it up. Run up. And then if I have this number, instead B6 is equals to 0, and then we round it down. And what does it mean by round it up here? Round it down is easy for this one. Round it down, it means that we just remove this number. And then it's just equals to, this is the approximation. And then we keep the 5 decimal points here. And that is the approximation. And what about the rounding up here? Rounding up here, because this is the binary representation, we need to add 1 to this number. And because we are doing some binary, this is the sum, binary sum or additions, and then it means that we add 1 to this phrase. Originally, this is 0, and then we add 1 to this phrase, and then it's just 1. And this is the rounding up way. And if we already have another number here, if we have, so for example, if we have a number instead of 0 here, and then we have 1, and then we have 1 in the 6th place. And how do we round it up? So because this one is 1, and then we want to round it up, and it means that we want to add 1 to this place. If we add 1 to this place, and then remember this is a binary representation, when we arrive at 2, and then we need to add 1 to the previous decimal place. This is the digit here. And then when this one arrives at 2, the number arrives at 2, and then we also need to get replace this one with 0, and then add 1 to the previous digits. So it means that, let us do the sum here. We are going to round it up so that we are going to add the 1 here. Actually, I'm adding the 0.00001. This is the binary representation. And I'm going to do the sum. This is one example here. I'm going to do the sum here. And it means that 1 plus 1, we have 2, right? But we cannot write 2 in the binary representation. We just change this 2 into 0. And then we add a small 1. This is something similar to the 10 base additions. And then we add a little 1 here in the previous digits. And then 1 plus 0. And then plus the extra 1 here, we get another 2. We reach to 2. And then whenever we reach to 2, we change the 2 to 0. And we do some extra things as well. We add a little 1 here in the previous, in the digits right in front of this place. And then so we have 1 little 1 here. So for this corner, we have 0 plus 0 plus the little 1. So for this corner, now we have 1. And then for the other things, it's just adding a 0. So this is 1, this is 0, and this is just 1. So now this is the rounding up. Does that make sense? This is some things we need to also make good use of something maybe you have learned before, the binary additions. When you reach to 2, and then you need to change the 2 to 0 here, and then add a little 1 to the previous, the places that is in front of this place. Does it make sense? Or any questions? This is the rounding up. You need to look into the places. If we want to round it into 5 places up to the decimal point, and then we need to look into the 6th place. If it is 1, and then we add 1 to the 5th place. And then you need to do some operations if there is some 2 appear. And then if the 6th place or the places up to the places you want, and then that is the 6th place in this example. And then if it is 0, and then we just remove the 0, and then we get the approximation. Does it make sense? So I have one formula for you, and then this is but this is in practice how we do it. And then the formula for it, how to do the rounding up, rounding down things. for the binary representation, this is the formula. So in base 2, and then this is the approximation of the x, and then this is the rounding, and chop, this is the chop or truncate. This is the d plus 1 and times the 2e. And this means that this is one general formula for the rounding up or rounding down. And in practice, we can do it in this way, or you can use the formula and we just add these numbers to the original numbers and then chop the places, chop the numbers, chop to the decimal places you want. So for examples, if we have this number and then we already simplify the example here, we take the e to be 0. And so now we only want 5 places after the decimal points, right? So now for these examples, we can also do it in this way. And it's the x, this is the x, 1.010100, and then plus the 2 to the, this is 2 to the negative, this is because we only want 5 places, so this is 6. So in the binary representation, we have 0.000001, and then if we do the binary additions here, we got at the end, we got 1.010101. And this is the precise numbers we get. But if we want to do the approximations and then we want to only keep the 5 places up to the decimal points, and then we just keep the 5 places up to the decimal point here. And that's the approximations number we want. And this is how you would use the formula to calculate it in the rounding up or rounding down. This is another way to do it. This is a general formula. Any questions? But a simple way to do it is just look into the places up to the digits up to the 5 places, the places you want. So we have 5 places, we want 5 places here, and then you look into the 6 places. And then if it is 1, and then add 1 to the previous point, previous digits. If it is 0, and then you just need to remove all the things after. And this is the easy way. And then you can forget about the formula. Any questions?
Where is the 2 to the exponent to the page, like times?
The exponential here?
Yeah, like where did you put it for the...
because I make it into a simplified format, and then I got this 2 number. It is just 2 to the 0, and then 2 to the 0. This is the simple example, and then this is 2 to the 0. And then it's just 1, so we can just ignore it for a moment. Rounding down? For this last 2 digits, why we get rid of this one, right? Because if you want to calculate with the formula, it means that you can first add the numbers here, and then that is times the 2 to the exponent 0. And then here we add it, and then we get this number, right? But we have 6 digits after the decimal point. And then now what we just want to keep 5 phrases. And then you don't need to know how to round it up, round it down here. You just need to chop all the things after the 5 phrases. Chop, truncate it, and then discard it after the some summations over there. This is another way to calculate the, to know how to round it up, round it down. This is a formula, but the easier way is to just look into the sixth place. Just look into the sixth place, and then if it is 1, and then add 1 to the previous digits. If it is 0, and then just discard it. So now let me get you another idea about the numerical methods. So a lot of time when you get approximations of a solution or a value, and you get error, and then how can we tell whether it is a good approximation or it's a bad approximation? Okay, let me give you one example. Example here. So we have 100. This is the number we have, x equals to 100. And the x equals to 99. This is the approximations to that number. And you will get the error. Maybe you can calculate the error in this way. X minus the x star, and then it's just 100 minus 99. And then the error is just 1. Maybe it's a good approximation, but let's do some comparison here. We have the number 1, and then we have the approximation. Let me see. We have the approximation 1.0001. This is the approximation. It should be y star. Maybe, let me change it. It's 1.1. This is the approximation of 1.1 for the y. This is the approximation number. And then this is the y itself. And then what's the error here? The error, we can do the subtractions and then take the absolute value. Absolute value, and then we get the error 1 minus 1.1. And then this is 0.1. So do you think this one had a better approximation, or do you think this one had a better approximation? Taking the error into the considerations, and then which one is a better approximation? Why is it better? Because the number is smaller.
Like the 1/100 is less than 1.1/1.
Yes, we cannot just take a look at the number here. We need to take a look at the percentage. Yes, we need to do the divisions over there. And let us take a look at if we divide this number by 1, and that is just 0.1. That is the 10% error here for the approximation. And then if we divide the numbers here by the exact value, and then that is the x. The x is just 100. And then this is 1%. This is just 1% error. So a lot of time, you cannot focus on the absolute error. Absolute error, it means that we take the absolute value of the difference, and then that means the absolute error. And what is the, and a lot of time, we need to focus on not the absolute error, and we need to focus on the absolute error divided by the exact value, and then we call this one is relative error, and then that is the percentage of the exact value. So let me give you the definitions here. So suppose we have 2 numbers, and this is the exact value, and then this is x, and then the approximations value is the x star. And then we define the absolute value, absolute error in this way. That is just the absolute value of the difference. The relative errors is the sign in this way. Relative error is the difference and then divided by the exact value. And this is the relative error. When we talk about the error in the numerical methods, most of the time we focus on the relative error because this is the true measure for the error. Any questions? We have 5 minutes left. Yes. Oh, it should be the whole number because the x could be negative, right? Yeah. We also take the absolute value for the x. Because it could be negative, but we only focus on the positive numbers, the 4 positive numbers for the error. So I think that's pretty much what we want to talk about this time. And just a beginning for this class. And if you have any questions, you can come over here to ask me. And if you don't have any other questions, and then you can feel free to get off.
What is it?
The is the places we want to give.
Oh, you mean for
Because-
this case is 5?
Yes.
So the D here is 5?
Yeah.
Oh,
So here we have so why I do the summation here. We do the summation here. We put the 0, 0, 0, 0, 0, 1. So this is a 6th place.
yeah. And what about the E of this case?
Oh, the E because I put it to the simple case, so the E for these examples
Oh, it's
are
a 0 because
Yeah.
times 1, right?
Yeah.
Oh, I see.
Hi, sorry. So I'm in a weird situation because I'm an exchange student here.
Uh-huh.
So I just want